4.1, 85 pages.
Yes, that's too much work! Oh my God, this is too much work.
Actually, my dear, you're not going to be doing much work at all. How can that be? In science, work is done when a force causes an object to move in the direction of the force. In this example, you may have put a lot of mental effort into doing your homework, but you won't be using force to move anything. The only work you'll be doing is turning the pages of your book. Is the archer doing work on her bow and arrow? She really is doing work on just the bow. She's moving the string back and it's traveling in the direction of her force. She's not doing work on the arrow. The bow provides the forward force to launch the arrow, and the arrow travels in the direction of that force applied. It's easy to see in the game of bowling how I'm doing work on the ball. However, I'm only doing work on the ball as long as I'm touching the ball. Once it leaves my hand, I will no longer be doing work on the ball because I'll no longer be applying a force to it. One way you can tell that I've done work on the hole puncher is that now the hole puncher has kinetic energy. This means that the hole puncher is now moving. I have transferred energy to the hole puncher, and now the hole puncher will work on the paper and transfer energy to the paper and produce a hole. Applying a force to an object doesn't always result in work being done. Do you think work's being done when the boys hold this bucket up? They're not doing work on the bucket because the bucket isn't moving in the direction of their force, and their force is up. If they lift the bucket up, like so, then they will be doing work on the bucket. But if they just hold it there, they're not doing work. Would you do more work on this car by pushing it up the long ramp to reach the top? Or by using a cable to raise the car up the side of the tow truck to the top of the ramp, both getting to the top of the ramp? You would certainly need a different amount of force. Common use of the word work may make it seem that there would be a difference in the amount of work done in these two cases as well. Let's assume this is kind of the same scenario, pushing the car up the ramp or lifting the car straight up the side. You may be surprised to learn that the same amount of work is being done to push the car up the ramp as it is to raise it right next to the tow truck. A certain amount of energy is needed to move the car from the bottom to the top of the ramp. Because the car ends up in the same place either way, the work done on the car is the same. However, pushing the car along the road up a hill seems easier than lifting it straight up. Why? The reason is that work depends on distance as well as force. Consider a mountain climber who reaches the top of a mountain by climbing straight up a cliff. She must use enough force to overcome her entire weight. But the distance she travels up the cliff is shorter than the distance traveled by hikers who reach the top of the mountain by walking up a slope. Either way, the same amount of work is done, but the hikers going up the slope don't need to use as much force as if they were going straight up the side of the cliff. This shows how you can use less force to do the same amount of work. The amount of work done in moving an object depends on distance as well as force. The formula for work is W equals F times D, where W is work and it's measured in joules, F is force measured in newtons, and D is distance measured in meters. So 1 joule will equal 1 Newton meter. If we look back to our mountain climber versus our hikers, path A would be the hikers and path B would be the mountain climber. Notice in path A that the F is lowercase. It's a small force for those hikers to get up to the hill, but it takes them longer to get up to that hill, as opposed to path B, which is the rock climbers. She is using a large force to raise her body against gravity, but she's going a smaller distance. F times D, F times D. They're going to equal each other, and you'll notice that the work will equal. They're getting to the top of the hill, the same position. They just go about the work two different ways. One feels easier because the force is less. That's the hiker's. One feels much harder, but it has less distance, which is the rock climber. Like the term work, the term power is used a lot in everyday language, but has a very specific meaning in science. Right now you see the little boy pumping up his bike tires with a straw. Not a lot of power. Power is the rate at which energy is transferred, or the rate at which work is done. Right now you see him using a small bike pump to pump up his tires. That's a little bit better. He's getting the work done faster. Now he's using a big bike pump to pump up his tires. Work is being done at a much faster rate. To calculate power, you divide the amount of work done by the time it takes to do that work, as shown in the following equation. The unit used to express power is joules per second. Joules per second is also called watt. 1 watt is equal to 1 joule per second. So if you do 50 joules of work in 5 seconds, your power is 10 joules per second, or 10 watts. Power measures how fast work happens, or how quickly energy is transferred. When more work is done in a given amount of time, the power output is greater. Power output is also greater when the time it takes to do a certain amount of work is decreased.